Now that we know what Bronsted-Lowry acids and bases are, which of course are proton donors for acids, proton acceptors for bases, there is another classification of acid and bases. We call those Lewis acids, Lewis bases. I think what you just need to know is that the Lewis acids will be lone pair acceptors, and the Lewis bases will be donating those electron pairs. The Lewis acids accepts the electron pairs, and the Lewis bases, of course, will be the donors. A good example, we usually use complexes of boron and aluminum. Of course, also iron can give you Lewis acids. I want you to check the Lewis structure of BF3 here. BF3. We're going to use that to explain why this is a Lewis acid. Remember, Bronsted-Lowry acids were proton donors. There's no hydrogens here, so there's no way you can make a proton, which is H plus, after dissociation. So we can't use that concept here. So that's why we define it as Lewis acid or Lewis bases. So here, the boron has 6 electrons around it. Each bond is 2 electrons. Is it octet stabilized? No. So it's missing 2 electrons, which means it can accept extra 2 electrons, and hence BF3 is a Lewis acid because it's gonna be able to accept electron pairs. And now same thing with AlCl3, okay, aluminium trichloride. The Lewis structure shows that aluminium does not have a lone pair. You have 6 electrons making the 3 bonds. So it can take 2 extra electrons to be octet. Same applies with iron tribromide or ferric tribromide. You have 6 electrons around the ion. So this central metal ion can take 2 more electrons, which makes it a Lewis acid. So what I've listed here are Lewis acids because that's gonna accept 2 more electrons to be octet. This is gonna accept 2 more electrons. This will accept 2 more electrons. All these 3 are Lewis acids. Okay, LA Lewis acid, not Los Angeles Lewis acid. Okay, so now what about the Lewis base? Lewis bases will be electron donors, and anything that has a lone pair on it, that is likely to be a Lewis base because this can take the role of a Lewis base because it can donate the 2 electrons, for example, to BF3. So let's say you are reacting BF3, which is a Lewis acid, and ammonia, which is a Lewis base characterized by the presence of a lone pair, because we said Lewis bases are electron pair donors. So these can donate the electrons. Again, we use double-ended arrow to show electron movement. So if these two react, you're gonna get a complex. Obviously, the nitrogen will get a plus charge because now the nitrogen will have 4 bonds to itself. We defined that nitrogen to be positively charged because nitrogen comfortably takes 3 bonds. Now, if it has 4 bonds, as what you have here, that nitrogen will take a positive charge. And of course, the bromine does not like to have 4 bonds. It likes 3 bonds like here. Because it has an extra bond, it's going to be a negative. Again, you can always use FC calculation to determine the formal charges. So when these two molecules react, the ammonia and BF3, you're going to get this complex with the nitrogen having a plus charge with the 3 hydrogens on it and an extra bond to the boron. So same applies here. If bromine, if the molecular bromine, the BR, if it attacks the ion center of FeBr3, you're going to get this complex. And again, there we needed to show a negative charge on the ion, and it's there. I think it's just faint. So you would use one of the lone pairs on one of these bromines to attack the ion. So you're donating the 2 electrons to this ion. Okay, you're gonna get this complex. So again, the bromine does not like having 2 bonds. It likes to have 1 bond. Again, if you want to know how to get a charge there, just do the math, because after using 1 lone pair, you'll be left with 2 lone pairs. Do the math, you'll find that this will take a charge of plus, and the ion will take a charge of minus. This bond right here used to be these 2 electrons. You remember a bond is made by 2 electrons? So that those 2 electrons were donated to ion, and they're kind of shared. Okay, so these 2 electrons are these ones here that were used to make the bond. So in summary, Lewis acids are electron pair acceptors. For example, this accepted the electrons. Lewis bases are electron donors. So this is a Lewis base. That's a Lewis acid, Lewis acid, Lewis acid. Ammonia is a Lewis base. Water can also be used as a Lewis base because it has lone pairs. But now notice that water can also be a Bronsted base, because Bronsted bases are proton acceptors. Like if you give it a proton here, water will take it, and that's how you'll make hydronium, H3O plus. We talked about it in the previous lecture. So this water, if it does this reaction, it's playing the role of a Bronsted-Lowry base, which are proton acceptors. It accepts an extra proton. That's why now there are 3, you started with 2. But the same water can play the role of a Lewis base, where it's just gonna donate the electrons to the boron to make a complex with 2 hydrogens and oxygen and a plus on the oxygen. So there are species that can play both the role of a Lewis acid or a Bronsted acid. So they can play the role of a Lewis acid or a Bronsted acid, Lewis base, or Bronsted base. So ammonia and water are perfect examples that can play both roles of Lewis base or Bronsted bases, because ammonia can pick up a proton. In that case, it's gonna play the role of a Bronsted base. But if it does what we just shown here, it's gonna take the role of a Lewis base. So Lewis bases are lone pair donors. Bronsted bases are proton acceptors. Okay. I think that settles it. So you need to just do more practice. It's not that obvious. You have to do more practice, and you're gonna get it right. Okay. Both boron, aluminium, and ion Fe can accept a lone pair of electrons, and that's why they're classified as Lewis acids. And the guys that are donating electrons like ammonia and water are Lewis bases. Even Br2 is a Lewis base because they can donate lone pair of electrons. Already. So I think next we'll start chapter 2.